One of the easiest ways to save time and effort when dealing with discrete probability calculations is making effective use of the discrete named distributions. The idea is that if you can identify the patterns where the different distributions are relevant, then immediately by identifying those distributions, you're going to be able to know what is the PMF, what is the expected value, what is the variance, and from there you can start to answer questions that are going to be of interest. And so instead of having to work from first principles, instead of having to think of the probability model or use combinatorics to determine different probabilities, you're going to be able to work from the known PMF or the known expected value or the known variance and solve the questions directly that way. This tends to save a lot of time and effort, and it's a really productive way of working through questions that are of interest. So once a named distribution has been identified, the PMF can be used in the same manner as any discrete distribution. So the PMFs of these named distributions are not special. They are just PMFs of discrete distributions. The only benefit is that by identifying the distribution that is being followed, we know what the PMF is automatically. Right, so what does this process actually look like? Well, to make effective use of the named distributions, we first identify the relevant distribution for any given scenario. And in particular, we're also going to want to identify the relevant parameters that characterize that distribution. So we're going to want to be able to say, this is the distribution it comes from, and based on all of the information we have, this is the parameter value or the parameter values that we care about. And as soon as we have done that, right, then we know the PMF, we know the variance, we know the expected value. Okay, so with the distribution and the parameters, we have all of the different components that we care about for these distributions. And then any probability question can be approached using the known PMF. At that point, the PMF is just like any other PMF, right? And so all of the rules of probability are still going to apply. All of our properties are still going to apply. The same thing goes for the summaries. The expected value and the variance is already known as well. But so then if we wanted to consider questions relating to those values, we're going to be able to use them directly as well. Okay, so let's just go through several examples that highlight why this is an effective tool for us to be thinking through. Okay, so 20% of bolts produced by a machine are defective. We want to determine the probability that out of 4 bolts chosen at random, that one of them is defective. Okay, and so we could work through this directly from first principles, but instead what we can say is, well, we have 4 bolts that we're looking at. Each one is either defective or it's not, and we know the probability that any bolt is defective is 20%. Okay, so we're counting up a fixed number of trials, right? We want to know the number of successes here, and so what we can say is that if X is going to represent the number of defective bolts, then X has to be a binomial random variable, right? And in particular, the parameters for the binomial are going to be the number of trials we're dealing with, so that is 4, and the probability of success for each of these trials. And in our case, a success is the bolt being defective, so that's going to be for 0.2. And so we want to know, well, what's the probability that one of them is defective? Okay, so that's the probability that X is equal to 1, which is simply the PMF with 1 plugged in. And so if we look back at our binomial PMF, that's going to be 4, choose 1, and then we take 0.2 to the power of 1, and 1 minus 0.2 to the power of 4 minus 1. Okay, we plug this in, and then that's going to give us our probability there. Right? So instead of having to try to work this out directly based on the probability model, we get immediately that things are binomial. Right? So we note the binomial of 4.2, so then the probability of 1 is going to be exactly plugged into the PMF, which gives us 0.4096, so 40.96%. Now, what's the probability that 0 are defective? Well, we've already identified the distribution here is the binomial 4.2 distribution, right? And so what we can do is we can just simply go back to our PMF here, right? So similar to what's going on with this, except instead of plugging a 1 in, we plug a 0 in, and that would give us the probability that there are 0 defective items. So we plug in 0 into our PMF, and it turns out that in this case, that's also 0.4096. Right? That's not always going to happen, but based on these numbers here, that does work out. So then, what if we want to know, well, what's the probability that fewer than 2 bolts are defective? And so again here, right, we want the probability that X is less than 2. Okay, and so if we think about, well, what is the possible ways that that can happen? That can happen if X is 0, or if x is 1. Right? Because these are disjoint events, we can simply add them up, right? It's the union of these two events. All of our rules from probability are still applying. The nice part is that we've worked out these probabilities above, okay? And so because of that, we're going to be able to say 0.4096 plus 0.4096 gives us the probability that we have 2 or fewer bolts being defective, right? So the probability that x is less than 2 is the probability that it's equal to 0 or 1. So adding up the PMFs, we get 0.8192. And so by identifying that this is binomial, we get the PMF immediately. These probability calculations become just plugging into a formula for us. Let's look at another example here. We have a collection of 20 comic books. They include 12 Marvel and 8 DC. If 7 comic books are selected at random and these are going to be sold, what is the probability that exactly 3 of them are going to be DC comics? Okay. Now, this is a question that is no different from an urn style question, right? We could have thought about this as being 20 balls in an urn, 12 are red, 8 of them are blue. What is the probability that 7 selected at random, exactly 3 are going to be blue? And you could work through that based on the equally likely probability model based on combinatorics. However, there's a much quicker way of us getting to the answer here, right? And the idea is that, okay, well, when we start picking out our comic books to sell at random, we're doing sampling without replacement, right? If you're going to sell your first comic, you can't then sell that as your second comic, right? And so we're sampling without replacement, and we're counting up how many of them are going to be satisfying the trait of being DC comics. And so as a result, we're dealing with a hypergeometric distribution, right? So x is going to represent the number of DC comics that are being sold. This is hypergeometric, and we're going to have a total of 20 comics, right? So this right here is n. Of those 20, 8 of them are DC, so that's the number of successes, that's m. And then we need to know, well, how many of them are being sold? That is 7, right? That is little n here, okay? And from these parameters, now we could answer any probability question that we want. In particular, we want to know, well, what's the probability that x is equal to 3? That is just our PMF with 3 plugged in, and our PMF is going to look like 20 minus 8, choose 7 minus 3, times by, and then we have 8, choose 3, divide that by 20, choose 7. Okay, and so this is the PMF of the hypergeometric, right, with the relevant parameters plugged into it. Okay? And so from there, we plug this in and we get our probability immediately. Now, if you want, you could work through the actual problem of trying to do this using the combinatorial arguments. And what you should find is that you get exactly the same answer, right? So x is going to follow a hypergeometric with a 28-7 distribution. We want the PMF with 3 plugged in, and so we get exactly this, which is going to give us 231 out of 646, or about 35.8%. So there's a 35.8% chance that of the 7 comics we're selling, exactly 3 of them are DC comics. Consider a third example here. So a traffic light at a certain intersection is green half the time, yellow 0.1 of the time, and red the remainder of the time. A car approaches the intersection once per day at a random time, and X represents the number of days until the car reaches 3 red lights. Okay, and so what we want to know first is, well, what's the probability that X is equal to 7? Now, in this case, we have to be thinking about, well, what is actually going on here, right? So the first thing to note is that we are going to be counting up the number of trials for Bernoulli experiments, right? Because each time the car approaches, we either get a red light or we don't. It's a success or a failure. And what we want to count up is how many of these do we have to experience until we have the 3rd red light, right? We're doing this up until we reach 3 red lights. And so as a result, right, when we're thinking through this, we have some set number of successes we're trying to reach. Each time is either a success or a failure. And so we're dealing with here a negative binomial distribution. Right, so we can say X is going to follow a negative binomial distribution. The number of successes we need to reach, that is R, is going to be 3. Right, that's when we stop. And each of the times we need to know, well, what's the probability of there being a success? Well, we need to know what's the probability that there's a red light. Right, so there's a 0.5 chance of it being green, 0.1 chance of it being yellow, and the rest of the time it's red. And so what we can do is we can say, well, that has to be 1 minus 0.5 minus 0.1, which is 0.4. right? So then x is negative binomial with 3.4. And so then if we want the probability that x is going to be 7, we take in the PMF with 7 plugged into it, okay? And so we can just walk through all of that here, right? We go, for this situation, the probability of the red light is 0.4. X is therefore a negative binomial with 3 and 0.4 as its two parameters. Right? Using the PMF, we plug in the 7, so that's 7 minus 1, choose 3 minus 1, times by 1 minus 0.4 to the 7 minus 3 times 0.4 to the 3, and that gives us 12.4416%, right? So about 12%, just over 12% chance that X is 7. So in other words, there's about a 12.4% chance that it takes 7 days for the car to see 3 red lights. Now, what is the expected value of X? So how many days should the car expect to pass this light before it has seen its third red light, right? The expected value in the case of the negative binomial is going to be R divided by P. So that's the number of successes we're looking for divided by the probability of success. In that case, that's 3 divided by 0.4, right? 3 divided by 0.4 happens to be 7.5. And so you should expect 7.5 days until you've seen the third red light. Let's take a look at another example here, right? The number of flaws in a given area of aluminum foil happens uniformly at a rate of 3 per square meter. If X represents the number of flaws in 1 meter squared random sample of foil, then what is the probability that X is equal to 5? Okay, so what's happening here? Well, what we're dealing with in this case, right, is we have this uniform or this constant rate of flaws that are happening, and it's a constant rate of 3 per square meter. We're dealing with a 1 meter squared random sample, and so we have a fixed interval here. We have a fixed constant mean rate, and so anytime you're counting the number of events over a fixed interval with a constant mean rate, you're dealing with a Poisson distribution. And so in this case, we have that X here is going to be Poisson, and the rate, we are told, is going to be 3 per square meter. So it's a Poisson 3 random variable. And so then if we want to know, well, what's the probability that X is 5? That is our probability mass function plugged in with 5. Right? So then we're going to have something like e to the negative 3 times by 3 to the 5. Divide that by 5 factorial, right? Because this is the PMF of the Poisson 3 distribution. Okay, so identifying that this is Poisson is going to give us the distribution we need here. So X is Poisson 3, so plug into the PMF. We get about 10%, right? 10.01% is the probability that X is 5. So what's the probability that X is 0? Well, we already know the PMF, and so we take 0 and we plug that into the PMF, right? It's going to be e to the negative 3 times 0 to the 5 divided by 0 factorial, and so that's just e to the negative 3. Right? So that's about 0.0498, so 4.98%. Now, what is the probability that there are any flaws? So again, here we can think about the fact that even though we have this as a Poisson random variable, all of our rules from probability still apply. We want to know, well, what's the probability that X is greater than 0? That's 1 minus the probability that X is exactly 0. And what we just found was that this is 1 minus e to the negative 3, right? We just found that the probability X was 0 is e to the negative 3. And so in other words, this is going to be, what, about 95%? Just over 95% based on the results from part B. Okay, so we have probability X is greater than or equal to 1 is 1 minus the probability at 0. So 1 minus the probability at 0 is 95.02%. Okay, so again, identifying that this is a Poisson, that it follows because we have this constant mean rate and we're looking at a specific area here, then we can deal with the Poisson distribution. That gives us the PMF that allows us to answer these questions a lot more straightforwardly. All right, let's look at one last example here. So a game is being played where the player is paid out based on the number of times that they can flip tails in a row. And every tail flipped, they're paid $5. So they're going to be flipping a coin, and each time they see a tails, they get $5. When they get a heads, the game is over. What is the expected payout of this game? Okay, so here we have to be a little bit thoughtful, right? So underlying this, there's some random variable that's representing how many flips of the coin do you see tails on before you see your first heads, right? Because if I told you, well, they flipped it 5 times and then they saw heads, you would know their payout has to be 5 times 5 So that's $25. So really what you care about here is counting how many tails you see, right? And so we're going to be flipping a coin. Every time you flip the coin, you either get heads or tails, and you keep flipping it until you see your first heads. Okay, so we're counting up the number of trials until our first success, right? In this case, the success is a flipping of a head. As soon as the first success happens, it's over. And so then we're thinking about the fact that there is a geometric distribution underlying things, right? So we can take x to be a geometric distribution, right? And x is going to be the number of flips until heads, right? The geometric distribution is characterized by a single parameter, which is the probability of success, which in our case is 0.5, because that is going to be the probability of getting a heads. Okay. Now, what we actually care about is not x, but it's going to be z. And what is z? Z is our payout. And so z is going to be $5 for every tail that we saw. The number of tails that we see is going to be x minus 1, right? Because every flip was a tail until our last flip, which turned up a head, right? So x is all of those flips. So x minus 1 is the number of tails. And if we just take 5 times this, that's going to give us the payout. And so what we want is the expected value of z, which is the expected value of 5 times x minus 5, right? Where we've just expanded out the 5 in here, 5 times x, and then 5 times negative 1, right? And what we can say here is that this is actually a transformation, a linear transformation of an expected value. And so because of the linear transformation, this is going to be 5 times the expected value of x minus 5. Okay, and so now we need to know, well, what's the expected value of x? But we know that x here is going to be a geometric random variable. And so the expected value of x is always 1 divided by p, which is 1 over 0.5, which in our case here is going to be 2. Okay, and so then this is going to be 5 times 2 minus 5, which is simply 5. Okay, so the expected value, the expected payout is going to be 5 here. Okay, so we'll remove that and then walk through that argument one more time here. All right, so what's the expected payout? Well, first we define x to be a geometric random variable that defines the number of flips, including that first head. So then x is geometric 0.5. Right? The payout is then z, which is 5 times x minus 1, so 5x minus 5. If we use transformation rules, then the expected value of 5x minus 5 is 5 times the expected value of x minus 5. And so if we work out exactly what that's going to be, that gives us 5 there. And so the expected payout is $5. Right? Now, if they have to pay $p to play, how much should they be willing to pay? So what is the maximum that they should be willing to pay? In other words, what's the fair cost for playing this game? Well, the fair cost for playing the game is always going to be the expected value of the random variable, right? So expected value of x is the, or the expected value of z in this case is the fair cost to play. And so in this case, it's going to be 5. We worked that out in part A. Now, what is the probability that they fail to earn money if they do pay $p to play? Right, so in other words, what is the probability that z is less than or equal to 5 if they willingly play, because they've paid the $p to play, right? So they've paid $5. So what's the probability that their payout is less than or equal to 5? Now, there's a couple of ways that we could think about doing this. We could try to solve this directly. We could also think about the fact of, well, what does this mean for x, right? So if z is less than or equal to 5, right, then we can say, well, if x is equal to 1, right, you get 1 flip. That means that you flipped ahead on your first trial. And so then your payout here is going to be 0, right? If x is equal to 2, that means that you got 1 tail and then you got your head. And so then x is equal to 5 here, or the payout's equal to 5 there. If x is equal to 3, that means that you got 2 tails, right, and then a head. And so then your payout there is equal to 10. Okay? And so only in these first 2 cases are they going to fail to earn money. Right? And so if they fail to earn money, that means that x was either 1 or 2. And if we want to know, well, what's the probability that x is 1 or 2? That's the PMF of x at 1 plus the PMF of x at 2. Okay, so that's our one approach that we can take to this question. And then you could solve that using the PMF of the geometric distribution. The other way that you can see this is by directly calculating this out, right? So we want the probability that z is less than or equal to 5, but we know z is just 5 times x minus 1. And so what we can do is we can just rearrange this equation, right? We divide both sides by this 5, okay? And so then we have x minus 1 less than or equal to 1 over here. But so then we can pull that negative 1 over there, and ultimately we're left with this probability that x is less than or equal to 2. Okay, and so then we get x being 1 plus x being 2, the exact same expression we worked out directly. And so if we want that, we plug into the geometric distribution, right? 1 minus p to the power of x minus 1 times by p. We add that up for 1 and for 2, and we get 0.75. So there's a 75% chance playing this game that they fail to earn money, or a 25% chance that they do earn money. Now, of course, this means that some of those times they're going to be earning $0, but still, with paying P to play, 75% chance you don't earn any money, and 25% chance that you do. Okay. So once you have identified the name distribution, you can then manipulate the PMFs, you can manipulate the expected values, you can manipulate the variances. And you can do this in the same way that you would manipulate any PMF or expected value or variance. All of the same rules apply. The only difference is that by identifying the scenario, you immediately know, well, what is the form of this PMF? And by knowing the form of the PMF, that's going to save a lot of time in trying to derive out the probabilities from scratch. Right, so this simplifies the process of computing the probabilities, it simplifies the process of computing the expected values, and allows us to focus on the actual material modeling of the situation instead. So being able to recognize when are the different named discrete distributions relevant, and then being able to quickly determine what is their PMF, what's their expected value, what's their variance, that's going to make discrete probability calculations far easier to deal with.